So, in the last section, we looked at the problem of bitmaps. We asked the question, can we learn the pixels of some textures to feed into a BRDF and get a desired output? In this section, we're going to start on the neural side and ask, can we learn a neural network that generates the pixels of a texture? So we'll start with the basic building block of any neural network, which is the neuron here. It's a nice and simple construct that's familiar to some, I'm sure. On the left-hand side, here we've got the inputs to the neuron, typically denoted the vector x, and a corresponding set of floating point weights denoted w, with one per input. We also have a bias, which is another floating point parameter, with one per neuron. And these are all fed into a simple linear equation which takes the dot product of the inputs with their corresponding weights and then adds the bias on the top. This linear equation gives us a value that's typically denoted z. And that linear value z is then fed into a non-linear activation function. And this is what lets our neural network solve non-linear problems. And the output of the activation function is the output of our neuron. We can also look at that maths in the center and instead represent it with code. All we're really doing here is taking a weighted sum of the inputs and then adding the bias on top, and then finally feeding the result through an activation function. So in other words, all we've got here is a for loop. To begin with, we're going to be looking at building the simplest possible texture network. In this system, we're going to be taking two inputs, the U and V we wish to sample, and we'll generate three outputs, the red, green, and blue components of the color. So on the left here, we've got our U and V inputs. These are fed into a red neuron to generate the red color, a green neuron to generate the green color, and a blue neuron to generate the blue color. So this network in total has got 6 weights and 3 biases. In other words, it's controlled by 9 floating point parameters. Diving straight into code, the slide might look a bit complex at first, but it's actually very similar to our earlier material parameters. We now have a network parameter structure. In this situation, we're also utilizing a nice little feature of SlangPy that lets us represent a slang structure with a corresponding Python class. Where our material had albedo, normal, and roughness, our network has biases and weights. And as we saw in Benedict's section, because we're going to be optimizing, our biases and weights also need corresponding gradients. Then we have accessors to read those biases and weights, and corresponding accessors that will write the bias and weight gradients. And finally, just to keep things clean on the Python side, we've added a helpful little optimize function to the network that feeds both the biases and weights and their gradients to the Atom optimizer. On to actually evaluating the neural network. We're going to start on the right-hand side, in which we take the UV and we store it as a simple array of just 2 arbitrary floats. We feed those 2 floats into the network, which gives us back 3 output floats. We apply our activation function to those outputs, and we return them as an RGB color. On the left-hand side, we've got that for loop that we saw earlier in the neuron diagram, which calculates the Z vector. And the only difference now is that we're doing it for all neurons instead of just one. So let's put that to some good use. At the top, we've got the lovely slang logo here for our reference image. Then we've got our render function, which is much simpler now than in the material case. All it has to do is calculate a UV, feed it into the network, and return the resulting color. And as you can see, because we've got an untrained network, what we get out is a brown smudge. And finally, the loss function, again, is much simpler than in the material case. It just has to generate a color from the network, compares the result to the desired color, and returns the squared error. And as you can see, for our untrained network, the loss is very big. So now let's train the network. In the material example, calculate grads was actually relatively complex, as we needed to generate all these random light directions for each pixel and recalculate reference colors and things like that. However, as we're just generating pixel colors now, all we need to do is call the loss function, which will push those gradients all the way back into the bias and weight gradient tensors. On the right-hand side, you can then see our optimization loop in which we just calculate those gradients and call optimize multiple times. And here's our result. It's not perfect, I'll admit, but let's take a little bit of a closer look at what's come out here. Our output on the right-hand side might at first appear to be a simple smudge, but we can actually see a kind of a gradient fill effect going on, where in the top left we've got this sort of reddish tint that corresponds to the top right red half of the reference image, and it is transitioning down to that kind of bluish color of the big blue disk in the reference image. So our network has come up with something, it's just not perfect yet. And if we stop and think about it, what we just asked our network to do was to try and solve with just 9 parameters and a bit of maths, the problem of approximating a 256 by 256 texture, which consisted effectively of about 200,000 parameters. And if you were to ask me to do that, then I would probably have come up with the same thing, which is a gradient fill. So how can we make this better? Well, the obvious answer is we need to add more parameters. So to do this, we're going to introduce 2 new hidden layers of neurons between the inputs and the outputs, each of which will contain 32 neurons. So now we're going to start with our U and our V. We'll feed those to our first hidden layer. Then we'll feed its outputs to the second hidden layer. And finally, we'll feed those outputs to the red, green, and blue neurons. So this network as a whole now contains 67 biases and 1,184 weights, a total of 1,251 floating point parameters. A lot more than 9, but still a lot less than the 200,000. So extending our slang program to support the hidden layers is actually pretty simple. We've now got 3 layers in the network structure. We take our inputs, we're going to feed them to layer 0. We'll take those outputs and apply the activation function. Then we'll feed those to layer 1. We'll take its outputs and apply the activation function. Then we'll feed those to layer 2, take its outputs, apply the activation function, and return the result, which is our color. And the Python side on the right simply allocates storage for those 3 layers and supports calling optimize on each one. And we've got progress. It's not there yet, but there's no doubt the network is now approximating the reference texture. We can see those kind of 2 big hero splodges in the center, and even most of the smaller stars are represented by either a red or a blue smudge. So now I'm going to hand over to Benedict to look at how we can get from smudges to something a little more like our reference image.